Okay, this is lesson 13, homework exercise 1, which is the simple linear regression. And then I'll do a separate video for homework exercise 2, multiple linear regression. Okay, so what we have here is 6 data points. So this 1 data point, 2, 3, 4, 5, 6 data points. And what it's picking up is the manufacturing line speed. So in other words, how fast is the line going, and the number of defective parts found. So this company believes that there's a relationship between these two, okay? So they devised a situation in which the same batch of parts was inspected visually at a variety of line speeds. So given that it's a visual inspection, their hypothesis is that faster the line goes, the less defects that are going to get spotted. So we're going to do an analysis of this data and see if that seems to hold true. So the first thing you have to do is develop a scatter chart with line speed as the independent variable. So that means X. So this is going to be X on the axis, and this will be Y on the axis. And then answer this question: what does the scatter chart indicate about the relationship between the two pieces, like the two variables? So line speed is going to be your independent variable on the x-axis, and number of defects is the dependent variable, meaning that the number of defects depends on line speed. So let's give it a show. Highlight the data like that. Hit insert. Go to this little scatter. Right? Grab that. Perfect. Slide it over so it's in the right spot. All right. So if we look at that data, we see here at slower speed. So remember, this is speed down here, and this is number of defects here. So if we look at this, it appears as though the faster the line goes, the less defects that are being picked up, because it's a visual inspection. It's about what you would expect to see. But what we want to see is the strength of this. Now keep in mind, we only have 6 data points, so it's really not enough of the sample size. I'd prefer to have at least 30, preferably 50. Data points, so we got a reasonable sample in order for us to draw any conclusions. But let's keep going. Something I want to do while we're right here is just click on one of these points so it highlights like that. Then right click with your mouse and add trend line. So click over here, display equation on the chart, and display the R² value. So let's pull this up here. And I will talk about what all these pieces mean here in a second. So don't forget that's there, we'll come back to it. So A, the answer to the rest of A, this scatter chart indicates there may be a negative linear relationship between line speed and number of defective parts found. So you can see that line is sloping down. The number of defect parts found is expected to decrease as the line speed increases. So the scatter chart is consistent with what would be expected. Okay, part B, use the data to develop an estimated regression equation that can be used to predict the number of defective parts found given the line speed. What's the estimated regression model? Well, we already have the equation, but I want to show you another way to get the same thing because we need some additional statistical information in order to look at the validity of those numbers. Okay, now we've got a fairly strong R², right? So again, we're going to look at some more data. So what you need here, go to data, data analysis. So I talked to you about this before. If you don't have this showing up out here in the margin, go to File, Options, Add-ins, and add in the Data Analysis Toolpack. And then it'll come back under Data. It should be there. Okay. So once you open that, click on Regression. So just plain old regression. And then we got to fix this up. So that one is actually perfect. That is the y-axis, and it's highlighting the right data. So we're good to go there. And then this one is perfect as well. All right, so those are the cell references that you want to have in there. That's exactly what we want. We want to put this in F37, so that's going to be fine too. So it's going to start right there. That'll work perfectly. And you want to make sure this residual plots is clicked. So if you don't have that clicked, make sure you do. Make sure you got all this just like this, and then say okay. Okay, so there's the regression output, right? I want to show you how this works. Pull this thing down here. and then we'll take a look at this. All right, so here's your R squared. What that's saying is, let me highlight it, roughly 74% of the variance in the data is being explained by the line speed. So this is what that's telling you, meaning that these data points aren't far from the line, right? They're not far from the line. Remember, if you get an R squared equal to 1, these data points would be exactly on the line. So it's when the points start showing some dispersion that the R squared value gets smaller, okay? Meaning that there's more variation in the data points for that data set. All right, so that's important. Then also, let's look at these. So what you got here is the y-intercept, and this is the slope, the x variable. So that's the slope. Let's confirm that that matches with the equation you put up here. So 22.174 is exactly right, and then the slope is negative 0.1478, and that's exactly what you see here. All right, so the additional information you got that's very helpful is right here. Okay, so this is saying that the intercept that you have here is, so let me explain. If the hypothesis is if the intercept is 0, so that's the hypothesis, the mean average of the intercept is 0, that would be the null hypothesis. So if you can reject the null hypothesis, then you basically are saying that this has a value greater than 0. It might be less than 0 too, but it has a value that's different than 0. So this is a two-tailed test, can be on either side, a value different than 0. And that's what we're trying to say here. We're trying to say that this independent variable, right, is having an impact on the number of defects that are discovered. So you want that slope in that line to be statistically significant, right? Statistically different than 0 is what we're saying. And so that way you can say, yeah, if there's a value there, then it has a relationship to driving the number of defects found. If this value is 0, so if I can't reject the null hypothesis, that's saying that this value is 0 and that this isn't having an impact on the number of defects found. All right, so let's keep going. The intercept is showing that I can reject the hypothesis and make the assumption that this value is not 0. Okay, that's what I'm interested in. Now this one, on the other hand, it depends. If I'm looking at a 1% level of significance, then I would say I can't reject this, meaning that I don't know if that's statistically different from 0 given the sample that I have. And one of my arguments here would be that the sample size isn't very big. Okay, sample size is not very big. So in order to really kind of beef this up and be able to draw any conclusions, I would suggest you get about 30 data points, or if you have a lot of outliers in the data, maybe go as high as 50 data points at least to get a better look at this and to improve the statistical significance of the variables. All right, so this one's not holding up for us, right? We can't reject that that's different than 0. Okay, so let's keep going. We've got to finish up this question, part B. What's the estimated regression model? All right, so we got to do that. The simple linear regression equation is y equals 22.1739, I'll just go 4 decimal places, minus 1478x. Okay, so that's your simple linear regression equation, meaning that if x were 0, that you had no defects, then if you had no line speed, then this number of defects would be 22, which really doesn't make any sense. And oftentimes the intercept doesn't make a lot of sense. In other words, it's just a value where this line will come back and hit this axis. And because it's outside of the range of potential speeds that you would have, you'd say that value is relatively meaningless. That intercept value. It's just a figure that lines up with this line, linear line that hits the y-axis. So it's not meaningful to us in terms of us making a decision with it. This would be, though, but it's not statistically significant at the 1% level. All right, let's keep going. So these are our residual, this is our residual output, and it's the plot that I'm most interested in looking at. So I'm going to go back and grab this, which I had given you during class, right here. I'm going to copy that, and I'm going to bring it over. Yeah. All right, so here's your conditions. The data points you see here have a mean of 0, and I would say that they probably do, right? This one is about as far away as this one is, so that zeroes out. This one is a little closer than this one, but they pretty much zero out. And these two are pretty close to each other, making up maybe a little bit of that difference you see here. So I would say, yeah, the mean is 0. They have similar variances. I would say, yes, that they have similar variances, right? They're within 1 or 2 rejections, no defects. They're concentrated around 0. I would say yes, right? So they're fairly concentrated. They're not way out, way away from the line. In fact, one's almost right on the line. All right, so I wouldn't say, so if we first check the conditions necessary for valid inference and regression, the Excel plot of the residuals and line speed are given above. Because we're only working with 6 observations, assessing the conditions necessary for that is extremely difficult. However, the scatter chart does not provide strong evidence of a violation of a condition. So that's the part right there that I'm talking about. That I don't see any evidence here in the scatter plot that violates these conditions. So that's what I'm talking about. So we'll keep going with our inference based on these p-values. So the p-value associated with the estimated regression parameter B1, so we call this regression parameter B1 right here. Oh, sorry, this is B1. This is B0, B0. I'd say B0. This is B1. Is 0.02813. That comes from right here. Because this p-value is greater than the 1% level of significance, we do not reject the hypothesis that B1 is 0. So we can't say with statistical significance that this number is different than 0. We conclude that there is no relationship between the line speed and the number of defective parts found. Okay, now let's look at B0. So this is B0 right here. The estimated regression parameter B0 suggests that when the line speed is 0, the number of defective parts found is 22.1739. That's this that we just talked about. This result is obviously not realistic, but the parameter estimate and the test of the hypothesis that B0 is 0 are meaningless because the y-intercept has been estimated through extrapolation, meaning there's no observation in the sample data with a line speed near 0. Okay, so that's part C. Hopefully that backs up what we just talked about. Part D, how much of the variation in the number of defective parts found for the sample data does the model you estimated in B explain? So it's asking you about the coefficient of determination, R squared. So remember we said earlier it's 0.7391. So the regression model estimated in part B explains approximately 74% of the variation in the number of defective parts found in the sample. Okay, so the model here we have isn't very good at predicting the number of defects given line speed, but in my opinion, a big part of the reason why it's not statistically significant is due to sample size. So I would rerun this with a larger number of data points if I could. All right, that's all I have for that one. So I'll start another video for the second one.